Alright, we're on to our last concept of the block, and for some people, this one's usually the most daunting one. Okay, but stoichiometry really isn't that bad as long as you are systematic about it. And this is why I've been trying to get you to do that dimensional analysis all block long. So, goal for today, you're going to learn what stoichiometry is, you're going to learn how the balanced equation is related to it, and how to spot a limiting reactant. So, stoichiometry is a process in chemistry. It is math related, so there is going to be some calculation involved here. And we use it to predict the amount of product that we're going to make, or we might use it to, determine how much of another reactant we need in order to use up what we have, that sort of thing. So it's calculations that help us, based on a balanced equation, determine how much we can make based on what we have. Okay, so the key is you have to have that balanced equation and then those coefficients, those large numbers in front of things. Like when you have 2H2 plus O2 makes 2H2O. It's these 2's out in front and then the invisible one here that we're going to be using with these stoichiometry calculations. Okay, so the first thing to get comfortable with stoichiometry is to understand molar ratios. And again, those come from those coefficients. Okay? So, when you're reading an equation, you have 2H2O plus 1O2 yields 2H2O. Okay? Those coefficients are telling you something. What it's saying is, for example, for every 2 moles of hydrogen gas, I need 1 mole of oxygen gas. Okay? My ratio would be a 2-to-1 ratio. Or what's going to help us in our dimensional analysis calculations is the fraction way of writing a ratio. So 2 over 1. Alright, you can also think about it the reverse way. For every mole of oxygen, I'm going to need 2 moles of hydrogen. Okay, so those are in a 1 to 2 ratio with each other, or 1 over 2. What you use these ratios for is when you don't have the number written in the formula, when you have a different number, you can figure out how much you're supposed to get. Okay, so for example, if I have 6 moles of hydrogen, how many moles of oxygen do you need? What you do is you do 6 moles of hydrogen, and it's like doing a conversion. Alright, so I know that from my reaction, I need 2 moles of hydrogen for every 1 mole oxygen. Okay, when it comes to writing the units inside your parentheses here, it's really important that you do include the molecule type. It's going to help with organization. It's going to prevent you from accidentally flipping this. Alright, because we need to cancel out moles of hydrogen to get to moles of oxygen. Okay? So what I end up doing is I have 6 divided by 2, so I'm going to need 3 moles of oxygen. Alright, this is simple enough, you might have been able to do that in your head. But as we get further into stoichiometry and you get, numbers that don't evenly divide, setting it up like this is going to make it much simpler for you. So a little bit more practice with that. Say we have 12 moles of aluminum, how many moles of oxygen do you need? So I have 12 moles of aluminum, and then I'm going to have to put my moles of aluminum on the bottom, so 4 moles of aluminum, and then 3 moles oxygen. Okay, so what I do here is I'm going to do 12 times 3 divided by 4. So that's going to be 12 times 3 is 36, divided by 4 is 9. So 9 moles of oxygen. Okay, try that again. If I have 6 moles of oxygen, how many moles of aluminum oxide? So this doesn't have to be just between reactants. You can use this with any 2 things in the reaction. So I have 6 moles O2, and then I'm going to put 3 moles of oxygen on the bottom, 2 moles of the Al2O3 or aluminum oxide, and that's going to give me, so my moles of oxygen cancel, 6 times 2 is 12, divided by 3 is 4 moles of the aluminum oxide. Alright, so pause the video, see if you can get the 2 for this next equation done. Then start it back up and see if you got it right. So go ahead and pause. Now that you have some answers to compare these two, I'm going to have, I always put what I know from my problem on the outside. I have 5 moles of iron chloride, FeCl3. And then iron chloride has an invisible 1 in front of it, so I'm going to have 1 mole FeCl3 on the bottom. And then I'm going to FeOH3, which also has an invisible 1 on it. So that gives me 5 times 1 divided by 1, which means I'm going to make 5 moles FeOH3. Okay. And then, again, just to double check my work, I did appropriately cancel out moles of the iron chloride. So next one, I have 9 moles NaOH. And then to cancel it out, I'm going to put the 3 moles of NaOH from the equation in here. Because we have that coefficient 3. Then we're going to FeOH3 again, so that's going to stay 1 mole. So here I'm going to have 9 times 1, which is 9, divided by 3, so 3 moles FeOH3. Alright, and just to double check my work, moles of sodium hydroxide did get canceled out. Okay. So, molar ratios, this is the new thing for stoichiometry stuff. So another thing related to stoichiometry is knowing your limiting reactant. So a reaction can only continue so long as you have both reactants still available. If you don't have the right proportion of reactants, you might run out of one before you use up the other. That one that you run out of is known as the limiting reactant. Okay, what it does is it limits your reaction. Once it's gone, the reaction doesn't continue anymore. So an example of this, taking that aluminum oxide equation. If I have 6 moles each of aluminum and oxygen, which one's going to run out first? Okay, so to do that, what I do is I just take that 6 moles and then divide it by the coefficient in the equation. So I get 1.5 from aluminum, and then 6 moles divided by 3 moles gives me 2 moles of O2. Alright, so what this is telling me is that I have enough aluminum to go through this reaction 1.5 times. I have enough oxygen to go through the reaction 2 times. So, based on that, which one's going to run out first? Aluminum, because I have less of it to actually run reactions with. Okay? So, once you've figured out what your limiting reactant is, if you have a question related to a product, what you're going to do is you're going to use that limiting reactant at the beginning of your stoichiometry. So we would go with 6 moles of aluminum at our start, and then the 4 moles of aluminum in the bottom, and the 2 moles Al2O3. Okay, so 6 times 2 is 12, divided by 4 is 3 moles of Al2O3. Okay. Alright, so one more set of practice. So if you have 4 moles of iron chloride and 6 moles of sodium hydroxide, what's going to be your limiting reactant? So you don't always necessarily have the same amount of each reactant, you might have different amounts, but the process is the same. I'm going to do the 4 moles of FeCl3, and I'm going to divide by the coefficient for FeCl3, which is 1. So that means I have 4 reactions to work with. All right, and then I have 6 moles NaOH, and I'm going to divide by the 3 moles in the reaction, which means I have 2 reactions to work with. Okay, so I have enough sodium hydroxide to run 2 complete reactions. When I say 2 complete reactions, it's really, tons and tons of reactions because it's 2 moles worth of reactions. But I'm just saying that to simplify the thought for you. And then I have enough FeCl3 for 4 reactions. So once I get through 2, I'm going to be out of NaOH. So that means I'm going to use the 6 moles of NaOH, because that's my limiting reactant, to figure out how much of the iron hydroxide I'm going to make. So 6 moles NaOH, to cancel that out, I'm going to put the 3 moles from the equation. So this molar ratio step right here always comes, the numbers always come from your equation, never ever from anywhere else. And then FeOH3 makes 1 mole because there's no number in front of it. So that is going to give me 2 moles, because it's 6 times 1 divided by 3, of FeOH3. So again, just to double check, I did appropriately set things up so that my moles of NaOH canceled out. So, these are a couple of practice problems for you. If you want some extra credit, email me your work and answers. And I hope this helped. If it didn't, make contact to come to a help session or something.